Let's talk about subspaces. A vector space V is a non-empty set of objects called vectors with two operations, addition and scalar multiplication, satisfying these 10 axioms. Here the vectors x, y, and z are in the vector space V, and c and d are scalars, that is, they're ordinary numbers. Here are the additive axioms. V is closed under addition, x plus y equals y plus x, that's commutativity. X plus y plus z equals x plus y plus z, it's associativity. 0 plus x equals x plus 0 equals x. 0 here is the 0 vector. The opposite of x plus x equals x plus the opposite of x equals 0. Here are the multiplicative axioms. V is closed under scalar multiplication. The scalar 1 times x equals x, and cd times x equals c times dx. And there are these two distributive axioms as well. For example, R sub n is a vector space. The set of all n-dimensional vectors satisfies those 10 axioms. P sub n, the set of all polynomials of degree less than or equal to n, is a vector space. P sub n is all polynomials of the form a sub 0 plus a sub 1t plus a sub 2t squared plus dot 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 plus a sub n t to the n. This is where the a sub I are in the real numbers. A non-empty subset of a vector space V is a subspace of V if it is closed under scalar multiplication and addition. A subspace is itself a vector space. For example, if V is a subspace of the vector space R3, prove it. Otherwise, explain why it is not. Let's take, for example, V is all vectors of the form AB0, where A and B are real numbers. Is that a vector space, or is it a subspace or not? First, let's prove that it's closed under scalar multiplication. If you take a vector of the form AB0, okay, let's just say you take a vector of the form AB0 and multiply it by scalar k. Notice what you end up with, Ka, Kb0. Hey, that's in V, because V consists of all vectors of the form something, something, 0. So it looks like it's closed under scalar multiplication. Now let's prove that it's closed under addition. Let's say AB0 and CD0 are in V. When you add them together, notice what you get. A plus C, comma, B plus D, comma, 0. You get something, something, 0. That's in V. V is closed under scalar multiplication and addition, so V is a subspace. How about V just consists of one vector, the 0 vector, 0, 0, 0. Is this a subspace of R3? First, let's prove that it's closed under scalar multiplication. Let K be an R. K times 0, 0, 0. Well, that's just 0, 0, 0. That's in the vector space. Now let's prove that it's closed under addition. When we add two vectors in V, well, there's only one vector in V, so you don't have a lot of choice here. But when you add two vectors in V, here's one vector in V, there's the other vector in V. You add them together, you get 0, 0, 0, and that's in V. V is closed under scalar multiplication and addition, so V is a vector space. How about V equals the vector 1, 2, 3? Just has one vector in it, 1, 2, 3. First, let's prove, or try to prove, that it's closed under scalar multiplication. Let K be an R. K times 1, 2, 3 is K, 2K, 3K. No, that's going to be in V only if K equals 1, because V has exactly one vector in it, 1, 2, 3, and this is in V only if K equals 1. The scalar multiple has to be in V for all scalars, so V is not a subspace. So we don't even need to see if it's closed under addition. It's not closed under scalar multiplication, so it's not a subspace. Recall that W is a linear combination of U and V if W equals AU plus BV for some scalars A and B. Let V1, V2, blah, 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 V sub k be an Rn. The set of linear combinations of V1, V2, dot, 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 V sub k is a subspace of R sub n. So that's another example of a subspace. For example, the set of all linear combinations of 1, 2, 3, and 4, 5, 6 is a subspace of R3. The set of all linear combinations of V1, V2, dot, 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 V sub k is called the span of V1, V2, dot, 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 V sub k, or simply span of V1, V2, dot, 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 V sub n. It is a subspace spanned by those vectors. Determine if 128 is in the span of 101, 214. Okay, this would mean that 128 is some scalar multiple of 101 and 214. In other words, it equals A times 101 and B times 214 for some vectors A and B. Let's see if that's the case. Is it true that 128 equals a times 101 plus b times 214? See, okay, that would imply that when we compare coefficients, we'd have 1 equals a plus 2b, 2 equals 0a plus b, and 8 equals a plus 4b. Let's rewrite it like this. Okay, and the reduced echelon form of this. So again, here we have a system of equations. Here's the augmented matrix for this system of equations. The reduced echelon form of that augmented matrix looks like this. Oh, I don't like that at all. Look at the solution. The solution is going to be a equals 0, b equals 0, and 0 equals 1. Yeah, I don't like that 0 equals 1 stuff. There is no solution. So 128 is not in the span of 101, 214. Determine if 416 is in the span of 101 and 214. This would mean that 416 equals a times 101 plus b times 214 for some scalars a and b. If we write it as a vector equation, we end up with that. Compare coefficients, we end up with this. So 4 equals a plus 2b, 1 equals 0a plus b, and 6 equals a plus 4b. Rewrite it like this, and the reduced echelon form of this system of equations is going to look like this. Oh, I like that. A equals 2, b equals 1, 0 equals 0. Hey, there is a solution. So 416 is in the span of 101, 214. More precisely, 416 equals 2 times 101 plus 1 times 214. Determine if 245 is in the span of 123. This would mean 245 equals some constant times 123 for some scalar a. This is not true, so the answer is no. 245 is not in the span of 123. Geometrically, what does the span of 123 look like? It is the set of all vectors of the form a, 1, 2, 3. In other words, it's the set of all vectors parallel to the vector 1, 2, 3. Geometrically, what does the span of 1, 2, 3, 1, 0, 0 look like? It's the set of all vectors of the form a, 1, 2, 3 plus b, 1, 0, 0. In other words, it's the set of all vectors which lie in a plane containing 1, 2, 3 and 1, 0, 0.